Hello guys, myself Sreyas, roll number 19. Today are here to present our project Driver Assistance Scene Context System, a real-time multi-label scene understanding for vehicles. My team members are Devananda and Gagan. This project focuses on enhancing driver assistance systems using computer vision and deep learning.
Let's dive into the introduction. Driver Assistance Systems, or ADAS, need to clearly understand the environment around the vehicle to ensure safe navigation. But real driving scenes are complicated because many conditions occur at the same time. For example, a vehicle can be on a residential road at night during heavy rain. Most traditional models only classify one label at a time, such as weather or road type. This is not enough for real-world driving. So, our project focuses on multi-label scene understanding, where the model predicts multiple attributes simultaneously. We use the BDD100K dataset, which is one of the largest real-world driving datasets.
The problem we address is, how can we build a system that can accurately identify multiple features of a driving scene at the same time? Specifically, our model predicts three attributes: weather, time of day, and scene type. The challenge is to make the model robust, fast, and accurate under a wide variety of conditions. This is especially important for self-driving cars and advanced driver assistance. For this, we use the BDD100K dataset, which contains 100,000 driving images collected from real roads. Each image comes with labels in a JSON format, so we first parsed these JSON files and extracted the attributes we needed. Then we cleaned the data and stored everything in a CSV file. Finally, we split the dataset into training, validation, and test sets, so the model can learn properly and be evaluated fairly. That concludes my part. I'll now hand it over to presenter 2 to explain our proposed approach.
Hello there, I'm Devananda. I'll first explain how we prepared the dataset and then how we built our model. The first step was data preprocessing. We took the CSV file that contained the labels and converted each category, weather, scene, and time, into multi-hot encoded vectors. This is important because each image can have multiple correct labels. Next, we resized every image to a fixed dimension and normalized it. We then created a custom PyTorch dataset class, which helps in efficiently loading and transforming images while training. These steps ensured that our data was properly structured for a multi-label classification problem. For the model architecture, we used a pre-trained convolutional neural network such as ResNet or EfficientNet. We replaced the final layer so that the output predicts multiple labels at the same time. For training, we used BCE with logits loss, which is the standard loss function for multi-label classification. Optimization was done using ADAM, which helps the model converge faster. We evaluated the model on metrics like precision, recall, and F1 score. These metrics give you a much better understanding of performance compared to just accuracy. This gives you a complete view of how we structured and trained our deep learning model. Now I will hand over to presenter 3 to discuss results and the conclusion.
Hey, I'm Gagan. I will be explaining the results section. In the results section, we show how our model performed on real test images. We observed that the model was able to accurately classify multiple attributes at once. For example, predicting rainy, city street, and night correctly for the same image. The visual results demonstrate good generalization across different lighting and weather conditions. This shows that the model is suitable for real-time driver assistance scenarios.
Weather classification results. First, we have the confusion matrix for the weather category. As we can see, the model performs very well on the major classes like clear, overcast, and rainy. For example, the model correctly identifies clear weather more than 820 times, with only small confusion with overcast. Snowy and foggy classes have fewer samples in the dataset, so we see slightly more misclassifications there, which is expected in real-world datasets. Scene type results. Next is the confusion matrix for scene type. The model does especially well on city, street, and highway, which have the most data. It also manages to identify more challenging categories like tunnel and gas station with high reliability. This shows that the model has learned diverse driving environments effectively. Time of day results. Finally, for the time of day classification, the model performs very strongly. Day versus night scenes are recognized with high confidence, and it even handles more subtle categories like dawn and dusk quite accurately.
Now, looking at the overall multi-label performance, our subset accuracy is 82.4%, which is strong considering the model needs to correctly predict all 3 labels simultaneously. Our macro F1 score is 84.3%, indicating balanced performance across all classes, and our precision and recall are both above 83%, showing consistent behavior across the dataset.
To conclude the presentation, we successfully developed a multi-label scene understanding system for driver assistance. The model can identify weather, scene type, and time of day simultaneously. We used real driving data from the BDD 100K dataset. Our approach based on pre-trained CNNs gave strong and reliable performance. Most importantly, this project demonstrates a complete pipeline from dataset processing to model evaluation. This system can be integrated into driver assistance or autonomous vehicle platforms to improve decision-making and road safety.
Thank you for your time and attention for listening the insights and findings of our project. We are now open to questions. Thank you. Thank you so much. See you in the next video. Bye.